Hi, on the first video of chapter 4, that was 4.1, I briefly discussed about how do we derive the equation of the motion, right? And then I considered four different cases. One is the equation of the motion with undamped vibration with no external force, undamped vibration with external force, damped vibration with no external force, and damped vibration with with external force, right? So this is the equation that I derived on section 4.1. The equation of motion for a damped spring mass system with external force is my double prime plus gamma y prime plus ky equals to ft, right? Where m is the mass of the object, gamma is the damping constant, right? And then k is the spring constant and f is the external force. With initial condition is y at 0 is y0 and y prime at 0 is v0. So where y is basically the distance of the spring from its distance of the object that is in the motion from its initial from its equilibrium condition, right? What is happening there is initially you have a spring, right, of certain length, and when you place an object at the bottom of the spring, then the spring will stretch a little bit, right? And then it will go up and down, up and down, up and down like that. It will vibrate, and ultimately it'll be stable. It'll just stay still at a certain point here, right? So when you attach the mass of the object of a mass m on the bottom of that spring, right? So this is the equilibrium position. That position is the equilibrium position. Before this object comes to the equilibrium position, it just goes up and down, right? Up and down, up and down. So you measure the length or the distance from this point. So this is y at t. So sometimes it goes up and then sometimes it goes down. So the downward direction we consider positive direction, and the upward direction we consider the negative direction, right? That's what we did. So if you have the spring and the object attached to the spring in certain media, for example, certain oil or water or anywhere else, if this system is happening in certain media, in that case we consider the damping. That is, the damping constant is gamma, okay? All right, so this spring has the spring constant k, and then ft is the external force. If you push that object, or if you leave it from, if you keep pushing that object using the certain forces like that, okay? So this is basically the equation of motion of the object of mass m that is attached to the bottom of the spring, okay? And then leave it to, or sometimes you push it and leave it, or sometimes you just leave it with initial velocity 0, right? Okay. And the initial conditions are these, okay? So I am going to consider several cases on this video and the next video. The first one is the undamped oscillator, no external force, okay? So undamped means there is no damping, so this gamma will be 0. You see that? This gamma will be 0, right? And no external force means this will be 0 as well. So how would the equation look like? The equation will look like my double prime plus ky equals to 0, right? Now how do I solve this equation? To solve this equation, we write the characteristic equation. How do we write that? M instead of y double prime, you write lambda square plus k. Instead of y, you don't write anything. So m lambda square plus k equals to 0. So if you solve this for lambda square, you subtract k on both sides and divide by m, you get lambda square equals negative k over m. Now if you find out lambda, then you need to take the square root. So you need to consider plus minus. But when you take the square root, you will get negative sign under the root. So you write I outside. That is the imaginary unit. So let us suppose that this value, let us denote by omega 0. Okay. or you say W0, we actually, this is omega 0. Omega 0 like this, okay? So I denoted that by omega 0. So basically the lambda value is plus minus I omega 0. But in the last section, you see that if the solution of the characteristic equation, or you can say that if the eigenvalues are complex, okay, if there are complex eigenvalues, or actually if there is a just imaginary eigenvalue, okay, the solution will be yt equals to c1 cosine omega 0 t, because that is I omega 0 plus and I omega 0 minus, right? And plus c2 times sine omega 0 t. By the way, if there was like mu plus I nu format, if there was mu plus minus I nu, then you will have like e to the mu t and then cosine like that, right? So that's the last section we discussed. Since it is just a purely imaginary, then this is how the equation look like, the solution of this equation look like, right? So to find out C1 and C2, you will use the initial condition, these initial conditions to find out C1 and C2. Okay, now I want to write this solution in slightly different form. We call phase portrait, phase amplitude form, okay? So what is the phase amplitude form? So what I want to do is I want to do some substitution there. So for C1 and C2, I want to write either in sine format or cosine format. So for C1 and C2, I'm assuming let C1 equals to R cosine delta and C2 is R sine delta. Then what would you write for YT? So YT would be, this is C1 cosine omega 0 t and then plus C2 sine omega 0 t, right? So if you take R out, it is like cosine delta cosine omega 0 t plus sine delta sine omega 0 t. So that will be cosine A cosine B plus sine A sine B. If you take R out, that will be cosine A minus B. So that will be basically cosine omega 0 t minus delta. You can write delta minus omega 0, not a problem, because cosine of a negative angle will be cosine. That's why you can write. So yt is equals to R cosine omega 0 t, omega 0 times t minus delta. It is called the phase amplitude form. This equation, this form of the solution is called phase amplitude form. But what is the value of R? How do I find out R? Look at this. This and then that. If you square this and then add this, what do you get? If you square and add, it will look like C1 square plus C2 square equals to R square, and then inside the parenthesis you will get sine square plus cosine square, right? Cosine square delta plus sine square delta, right? So what is the cosine square plus sine square? So this will be 1, so you will get R square equals C1 square plus C2 square, and then R will be, if you take the square root, you will get R equals to under the root C1 square plus C2 square. That's what you get, okay? Also, if you divide C2 by C1, what do you get? C2 divided by C1 will be R sine delta over R cosine delta. So R and R will cancel out, so you will get tangent delta, right? That's what you get. So tangent delta equals to C2 over C1. Now, if you solve for delta, what do you get? Delta will be tangent inverse C2 over C1. So the delta can be one of these depending on the sign of C1 and C2, okay? So for example, here, if both C1 and C2 are positive, then that will fall in the first quadrant, right? This will fall in the first quadrant. So tangent inverse C2 divided by C1, that will happen, okay? If C1 is negative, then that value will, delta will fall in either second quadrant or the third quadrant, right? Because it will be like first quadrant is both positive, and this and that will be one of the value positive. So C1 is negative, okay? So it's like C1, C2 like this, right? So if both are positive, that fall here. If C1 is negative, this will either fall here or here. If C1 is positive but C2 is negative, so if C1 is positive, C2 is positive here. If C1 is positive, C2 negative in the fourth quadrant, right? So it is like, so this is the second and third quadrant case. When C1 is negative, then you will find out pi plus tangent inverse C2 over C1. This, and if C1 is positive but C2 is negative, then this will fall in the fourth quadrant. Then the answer will be 2 pi plus tangent inverse C2 over C1, okay? If C1 is 0, that means right here, and then if C2 is positive, it will fall here. How do we find? That is pi over 2. and if c2 is negative, that will for here, that angle will be negative pi over 2, that is 3 pi over 2. So that's the value of delta. Okay guys, now so we want to define some terms from this phase amplitude form, from this form. Okay, the local max or local, so let me tell you this. If you plot this equation, okay, you will get the graph of this form. Okay, because there is no damping, meaning that so what is happening is the concept is this. Let me show you what is happening. So whenever, if there is no damping, then that spring will keep vibrating, right, going up and down, up and down, up and down. It's like doing like this all the time, right? Up and down, up and down. So how do you write that? Up, down, up, down. So this is what I'm drawing the graph in with t along the x-axis. Okay, so t, and this is y of t. So this is what the plot look like. Okay, since there is no damping, then the object keep moving, so keep oscillating with the same height. So the distance between the two highest local highest point or the two local lowest point, that is called so that is called the period of the motion. Okay, that is the period of the motion. We denote by t, and it is given by 2 pi over omega 0. Okay, so the period is given by 2 pi over omega 0, which is equals to 2 pi under the root m over k. Because what is the omega 0? Omega 0 is root under k over m, right? If you divide by omega 0, then it will be m over k times m over k. So this is the formula to find out the period of the motion. All right. So the next one, so the period will be measured in the radians per unit time. All right. And omega 0 is k over m, is called the circular or natural frequency of vibration. That omega 0 is called the circular or natural frequency of vibration. Okay guys, next is the maximum displacement r of the mass from equilibrium is called the amplitude. So this is the equilibrium line. So you see that whenever this object vibrate up, down, up, down, up, down, this is the equilibrium position. Before it comes to the equilibrium position, it is like up, down, up, down, up, down. So this line, horizontal line, is the equilibrium position. Okay, now the maximum displacement it goes is that height or that height, and the minimum displacement it goes is that height, right? That down it can go. So that is called r. Okay, the maximum displacement or the minimum displacement, that is called r. You see that is r, or this one is r. Okay, so it is called amplitude of the motion. That r is called amplitude of the motion. So we saw the period and the amplitude of the motion. The quantity delta, this quantity delta, okay, delta is called phase or phase angle, which is shifting needed to overlap releasing from equilibrium position. What does that mean? That means if you release the object like from here, then the motion will be like go down and then up, down, up, down, up, like that, right? So if you release the object like little pulling down and then release it, it will start like this, right? So it will show like this. This is the motion. This is the plot for yt. You see that? Now, okay, let us see this one. So look at this. So here it is going down and then up and then down, up. So it is going up and then down and up, right? So these are basically the graph of the motion, right? But you see that how far do I need to push it? How far do I need to shift to the left to exactly overlap with that? Look at this. So here, whenever it is going down, this is the point where it crossed the equilibrium point, right? Or the equilibrium position. But whenever it is going down and then going up and then going down, how far should I push? You should push this. This is the time, because you are plotting against time here, right? So you are plotting against time. This is t. This is t. So you need to push that time left, okay? we call that is the phase time. Okay, this is called the phase time, but we'll have a slightly different formula. I will discuss that later. But delta is the phase or phase angle. Just the delta we measure in terms of angle, radian, okay, which is shifting needed to overlap with the releasing from equilibrium position. Okay, that is we denote by delta. So let us see. So I will define the phase time next, and then I will give you a couple examples on this. Okay, guys. So delta is called phase angle, but if you divide delta by omega 0, we call time shift. Okay, it is called time shift of the wave from its normal position corresponding to delta equals to 0. So how much time is that difference? If you want to overlap this with that one, okay, how much time before or after you should start with. Okay, all right. So let us see one example on finding these quantities t, r, delta, all those quantities. Okay, so the question is find omega 0, r, amplitude, okay, and the delta if the solution of an equation of the motion is given in that form, right? So what is the standard or the general solution we got? We got y equals to c1 cosine omega 0 t, right? And then minus c2 or plus c2 sine omega 0 t. That's what we have the formula, right? So what is the value of omega 0 here then? So here omega 0 will be, if you compare that, you got omega 0 is 3, right? So what is C1? C1 is 4 and C2 is negative 2. You see that? So what will be R then? So that R will be under the root C1 square plus C2 square, right? So it will be 16 plus 4. That will be, so 2 square root of 5, right? Because 16 plus 4 is 20. 20 is 4 times 5. So 4 square root of 4 is 2. So 2 is square root of 5. That's what you get. And now how do I find out delta? Delta equals to tangent inverse C2 over C1, right? So how much is that? Tangent inverse. So what do you get? So which one is positive? Which one is negative? C2 is negative and C1 is positive. So it should be in the fourth quadrant, right? So let's do C2 over C1, negative 2 over 4. That's what you get. That is, you will get tangent inverse. I would write negative tangent inverse 1/2, right? So I don't have the exact value. So I want to keep like this. I want to keep that way. Okay. So negative tangent inverse 1/2. If you know if you have the exact value for 1/2 for tangent, for example, if it was root 3 or 1 over root 3 or 1, then you do 2 pi plus for the fourth quadrant, because I wrote the formula before, right? So so it will be negative tangent is pi over 2. So what would you write? So you would write the phase amplitude form. So the phase amplitude. So you want to also write the phase amplitude form. Phase amplitude form will be yt equals to r is 2 root 5, right? And then cosine, right? And then what is that? What is the formula? Omega 0 t. So r cosine omega 0. Oh, I'm sorry. Omega 0 t. Omega 0 is how much? 3, right? 3t. And then minus delta, but minus will be plus tangent inverse 1 over 2. This is what you get. So this is the phase amplitude form of that equation, of this given equation. Okay, of this given equation. Okay, so let us talk about another example. That will be the last example that I'm giving you on this. Let us look at this example. What it says here is a mass of 2 pounds stretches a spring 6 inches. You see that it is given in the inch. So we'll have to change it. We'll have to change this into feet. Okay. If a mass is pulled down an additional 3 inches and then released, and if there is no damping, determine the position of mass at any time t. Plot y versus t. Find the frequency, period, and amplitude of the motion. Okay, so you want to find out all those things that you found on this example. Okay, So let us first list the given things. Okay, what is given? W is given as 2 pound, right? So it was pulled down. L is given as 6 inch, which is given, which is basically 1/2 feet, right? And a mass is pulled down an additional 3 inch. So what is y prime? So y at 0, not y prime. Y at 0 is basically given as 3 inch. 3 inch is 1/4 feet, right? And what is y prime of 0? It is released after it's pulling. It is releasing that, right? So it will be 0. This is given. Okay, guys. So what we need to find out here is there is no damping, means gamma equals to 0. So we will be using that equation that we discussed. Okay, so there is no gamma, there is no external force, F equals to 0. So you will have the equation like m y double prime plus ky equals to 0. Okay, so we want to do that. So first of all, let us find out k. So how to find out k? What is the formula for w? W is equals to k times L, right? So what is W? W is given as 2, and then K is K. L is 1/2, right? So what do you get for K? K is 4, okay? 4, I would say, if you want to write down the units, 4 pound per feet. That is the spring constant, okay, guys? Now, I want to find out the mass of that object. So it will be W is equals to m times g, right? What is W? W is given as 2, right? 2 equals to m times g is 32, right? What is m then? M will be 1/16. That is the m. Okay. So what is the equation of motion then? So equation of motion is it will be m y double prime plus ky equals to 0, right? So you get 1/16 y double prime plus k is 4, right? Y equals to 0. Okay, let me write down the things here. So you can write y double prime plus 64y is equals to 0. So what I'm doing here is I'm basically multiplying all these terms by 16. Okay, now so what I want to do is I want to basically write down the solution there, right? So how would the solution look like? I want to write the solution. I mean, you can write the solution in either form, because we have the two forms of solution. One is the general solution and another is the phase amplitude form, right? Another is the phase amplitude form. So let us first find out. Let me write down the initial and the actually let me write down the initial condition. Y at 0 is equals to 3 inch, that is 1/4 feet. And then y prime at 0 is equals to 0, right? 0. This is what you get. Now let me find out because you know that what is the equation, because how should we do this is you need to write down the characteristic equation, right? And find out the value of lambda, and then write the final solution. But you don't need to do here because we know the formula already, right? In this case, what is the general solution? Hence the general solution is you can write y of t is equals to what? C1, right? So you write C1 cosine of omega 0 t, right? And then plus C2 sine of omega 0 t. You see that? We will find out C1 and C2 by using this initial condition. But what is omega 0 first? Let us find out the omega 0. What is the formula for omega 0? Where omega 0 is equals to, what is the formula for that? Under the root k over m, right? We derive that. So what is our k? K is 4 under the root 4 over m is 1/16. So what do you get? You will get under the root, if you write the 4 times 16 over 1 will be 64, that is 8. So what is the equation look like? Y of t is equals to C1 cosine 8t, right? And then plus C2 sine 8t. This is what you get. Now I want to use the initial condition. So initial condition is y0 equals to 1/4. So let me use that. You can write t equals to 0, 1/4 equals to C1 cosine 8 times 0 will be, cosine 0 is 1, right? And plus C2 times sine 8 times 0 is 0. So sine 0 is 0. So C1 is basically 1/4. How about, let us find out y prime. Why? Because I need to plug in that y. I want to use that y prime of 0 equals 0. Y prime equals to 8C1 negative 8C1 sine 8t, because the derivative of cosine is negative sign. That's why I wrote negative. And then you need to find out the derivative of inside thing, right? It is like cosine u. What is the derivative of cosine u? It will be negative sine u times u prime. That's u prime will be 8. That's why I wrote negative 8 there. And then plus 8c2 cosine 8t, because the derivative of sine u will be cosine u times u prime. That u prime makes it 8 there, okay? So that is for t. But if you take t equals to 0, you will get 0 equals to negative 8 sine 0 will be 0, right? Because 8 times 0 is 0, so sine 0 is 0. And then plus 8 c2 and cosine 0 is 1. So what is c2? c2 is also, c2 is 0, right? You got c1 is c1 is 1/4 and c2 is 0. So what is the final version of the solution? Hence you get what? Yt equals to 1/4 cosine 8t. That's it, right? That is the solution. That is the final solution. So if you want to plot, you can easily plot this. Where do you want to plot it? You want to, there are several software. You can plot in the calculator, or you can plot in the Wolfram Alpha, okay? And then if you plot this, what you get there is you will get a graph. Let me draw it here, okay? So your graph will look like this. Your graph will look like, okay, if you plot between 0 and a number, your graph will like this. This is roughly, this is what it looks like, okay? So but the question asks you to find out the period, okay? Because we already find out the omega 0, right? That is the frequency. And then we want to find out the period and amplitude. What is the formula for period? Period is t equals to 2 pi over omega 0, right? So 2 pi, what is omega 0? 8. So that will be pi over 4. And also, what is the amplitude? Amplitude is under the root c1 square plus c2 square, right? What is c1 square? c1 is 1/4 and c2 is 0, right? So what will be, that will be 1/4 square. That is just 1/4. That's what you get, okay? This is how you solve the spring mass system problems if there is no damping and there is no external force, okay? Thank you.